Hello everyone, very good evening to all of you. Good evening everyone, good evening. So am I audible and visible? So please let me know in a chat box. Good evening, good evening. Voice is clear, video is clear. Okay, so shall we start today's session? So beta, whatever we discussed in the previous class, that is clear to everyone, right? In previous class, we discussed about the viscosity, right? In previous class, we discussed about the viscosity, and also we discussed a very important law in fluid mechanics, and that is a viscosity, that is a Newton's law of viscosity, right? So basically, what is the viscosity, right? What is a viscosity? So viscosity is nothing but it is a fluid property. Because of that, it offers the resistance against the flow, or we can say in a more technical way, right? Viscosity is a fluid property. Because of that, it offers resistance against the shear deformation, right? The shear deformation is nothing but the flow only. So what is the viscosity? Viscosity is a fluid property. Because of that, it offers resistance against the flow, or you can say resistance against the shear deformation, right? And because of the viscosity, the fluid layer experiences the frictional force, or you can say resistance force, or you can say shear force, when the layers are trying to move each other, right? And also we discussed that though viscosity is a fluid property, but viscosity come into picture when fluid is in motion, or we can say though viscosity is a fluid property, but the action of viscosity, we can see when the fluid is in motion, right? And also we discussed that when we are talking about the ideal fluid, right, if you classify the fluid in a very basic manner, if you classify the fluid, then there are two types of fluid. One is the ideal fluid and second one is a real fluid, right? Right now forget about the Newtonian, non-Newtonian or another classification. Here I am talking about the very basic classification. So if I am talking about the basic classification of the fluids, so fluids are two types. One is the ideal fluid and second one is a real fluid. So what is the basic difference between the ideal fluid and the real fluid? In case of the ideal fluid, there is zero viscosity, right? If I'm talking about the ideal fluid, in case of the ideal fluid does not experiences any resistance against the flow. So we can say in case of the ideal fluid, the viscosity is zero. Whereas in case of the real fluid, right, definitely some viscosity is present, right? Now, if I'm talking about the viscosity in any fluid, right, in any fluid, what are the factors which are responsible for the viscosity, or what are the, I can say, in any fluid, if I am talking about the reason of the viscosity, so viscosity, there are two factors which are responsible for the viscosity. The first factor is the intermolecular attraction between the fluid molecules, right? Intermolecular attraction between the fluid molecules, that is called the cohesive force, right? We already know, if I'm talking about the intermolecular attraction forces, so there are two kind of intermolecular attraction forces. One is the cohesive force and second one is the adhesive force. Can anyone tell me what is the difference between the cohesive force and the adhesive force? Can anyone tell me what is the difference between cohesive force and the adhesive force? Right. So if I'm talking about the intermolecular attraction between the same molecules, right, between the same molecules, that is a cohesive force. But if I'm talking about the intermolecular attraction force between different molecules, then that is a adhesive force, right? But here, what is the reason of the viscosity? What is the reason of the viscosity? That first reason is the intermolecular attraction force between the same molecules, so that is a cohesive force, right? The second factor is the molecular momentum exchange, right? The momentum exchange between the molecules is the second factor which is responsible for the viscosity. So in any fluid, the viscosity is because of the two factors. First factor is the cohesive force and the second factor is the molecular momentum exchange, right? After that, we discuss about the Newton's law of viscosity, right? After that, we discuss about the Newton's law of viscosity. So what is the Newton's law of viscosity? So as per Newton's law of viscosity, we can say, right, the shear stress experienced by the fluid layer is directly proportional to the shear strain rate, or we can say angular deformation rate, right? So as per the Newton's law of viscosity, as per Newton's law of viscosity, as per Newton's law of viscosity, right, the shear stress experienced by the fluid layer, shear stress experienced by the fluid layer, shear stress is directly proportional to shear strain rate, or we can say angular deformation rate, or we can say angular deformation rate, right? So shear stress is denoted by tau, and the rate of angular deformation is denoted by d phi by dt, So we can say tau is directly proportional to, d phi by dt. And when you remove the proportionality sign, then proportionality constant come into picture. So we can say tau is equal to constant multiplied by d phi by dt. And this constant shows the material property. And which kind of material property? A material property which offers the resistance against the fluid flow, right? So this constant is a material property, and this material property is known as the viscosity, or coefficient of viscosity, or absolute viscosity, right? Or you can say dynamic viscosity, right? So we can say tau is equal to, that is mu d phi by dt, right? So this is the mathematical expression of Newton's law of viscosity. Right? In yesterday's class, we also proved that this d phi by dt, right? This d phi by dt, in previous class we also proved that this d phi by dt is equal to du by dy, right? D phi by dt is equal to du by dy. And beta, what is the du by dy? This is the velocity gradient. Velocity gradient in y direction. Right? So we can write very famous Newton's law of viscosity mathematical expression, that shear stress at any y is equal to mu du by dy at that y, right? So this is the mathematical expression of Newton's law of viscosity. Famous, or I can say popular mathematical expression of the Newton's law of viscosity. This is also a mathematical expression of Newton's law of viscosity, but this mathematical expression is more popular because your experiences the number of numerical problems, and that numerical problems are solved by this equation, right? So what are the limitations? If I'm talking about the limitation of these equations, so what are the limitation, or if I'm talking about the validity of this expression, so what are the cases in which this expression is applicable? So first, the flow must be laminar flow. So this expression is applicable when the flow is laminar flow. Also, this expression is applicable when the fluid is Newtonian fluid. Right? And also the third important thing, that u is only function of y. Then we can use this mathematical expression. Right? So you should remember these three conditions. Okay, now what is the Newtonian fluid? What is the Newtonian fluid? So obviously a fluid which follows the Newton's law of viscosity, right? A fluid which follows the Newton's law of viscosity, that is called the Newtonian fluid. And if I'm talking about the examples, so there are a number of examples: air, water, kerosene, petrol, benzene, right? These are the example of the Newtonian fluid. Okay, now come to the unit part, right? Come to the unit. What is the SI unit? What is the SI unit of viscosity? What is the SI unit of viscosity? What is the SI unit of viscosity? Right? Tell me, what is the SI unit of viscosity? So SI unit of viscosity is, you can say Pascal second, or you can say Newton second per meter square. So this is the SI unit. Now if I'm talking about the MKS unit, if I'm talking about the MKS unit, I'm sorry, this is mu, na. If I'm talking about the MKS unit, so that MKS unit is kg per meter second. And what is the relation between SI unit and the MKS unit? What is the relation between SI unit and the MKS unit? So we can write that 1 Newton second per meter square is equal to 1 kg per meter second. Right? So this is the relation between SI unit and the MKS unit. Next, if I'm talking about the CGS unit, so what is the CGS unit of viscosity? What is the CGS unit of viscosity? So CGS unit is poise. The CGS unit is poise. CGS unit is poise. And what is the poise? Poise is nothing but the dyne second per centimeter square. Right? What is the poise? Poise is nothing but the dyne second per centimeter square. So we can say 1 poise is equal to 1 dyne second per centimeter square. Right? Now, if I'm talking about the relation between the SI unit and the CGS unit, right? If I'm talking about the relation between the CGS unit and the SI unit, so we can say 1 poise is equal to 0.1 Newton second per meter square, or we can say 0.1 kg per meter second. So this is a very important relationship, right? 1 poise is equal to 0.1 Newton second per meter square, or you can say 0.1 kg per meter second, right? And we also discussed the shear stress versus shear strain rate plot for the Newtonian fluid, right? Shear stress versus, we also discussed in previous class, shear stress versus shear strain rate. Shear stress versus shear strain rate. Shear stress versus shear strain rate plot for Newtonian fluid. Okay, so this is the shear stress axis, shear stress, that is tau, and this is the shear strain rate, shear strain rate, and this is the d phi by dt, right? D phi by dt, right? And for the Newtonian fluid, this is the graph. For the Newtonian fluid, this is the graph, a straight line, right? Newtonian fluid. And this slope, right? This slope of this line represent the dynamic viscosity. Or you can say viscosity. Right? Can anyone draw the shear stress versus shear strain rate plot for the ideal fluid? Can anyone draw the shear stress versus shear strain rate plot for the ideal fluid? For the ideal fluid. For the ideal fluid. If I am talking about the shear stress tau versus d phi by dt graph for the ideal fluid. Can anyone draw? Can anyone draw? Can anyone draw? Very good, beta. Very good, very good, very good. So if I'm talking about the ideal fluid, if I'm talking about the ideal fluid, if I'm talking about the ideal fluid, so we know that in case of the ideal fluid, that viscosity is 0. We know that in case of the ideal fluid that viscosity is 0. And viscosity is 0, that means the fluid layer does not experiences any shear stress. So tau is equal to 0. Right? So tau is equal to 0. 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 That means x-axis. That means x-axis. So this is the graph for the ideal fluid. This is the graph for the ideal fluid. This is the graph for the ideal fluid. Can anyone draw the graph for the ideal solid? Can anyone draw the graph for ideal solid? Can anyone plot the graph for ideal solid? Ideal solid, beta. Ideal solid means perfect solid. Ideal solid means perfect solid. Perfect solid means rigid body. I am talking about the rigid body. Right? Ideal solid. Perfect solid. Perfect solid means there is no deformation, or I can say there is no relative change in position of the particles. There is no change in relative position of the particles. So if I am talking about the ideal solid, so in case of the ideal solid, no change, or I can say deformation is equal to 0. Right? In simple word, I can say deformation is equal to 0. Deformation is equal to 0. Right? So deformation is 0. So in which axis deformation is 0? In which axis deformation is 0? In a y-axis. So beta, this is the graph for the ideal solid, or you can say perfect solid. This is the graph for the ideal solid, or you can say perfect solid. Right? Is it clear to everyone? Is it clear to everyone? So whatever we discussed, that is clear to everyone? That is clear to everyone? Okay, now come to the next topic, that is a viscometer. Right? Come to the next topic, that is a viscometer. So what is a viscometer? So beta, basically viscometer is a device which is used to measure the viscosity. Simple. Right? What is a viscometer? Viscometer is a device which is used to measure the viscosity of a fluid. Now, if I'm talking about the type of viscometer, right, there are different types of viscometer. Right? If I'm talking about the viscometer, there are different types of viscometer. The first viscometer is rotating cylinder viscometer, or we can say rotating disc viscometer, right, or concentric tube viscometer. Right? Rotating cylinder viscometer, or rotating disc viscometer, or concentric tube viscometer. Right? These viscometer based on the one principle. Right? If I'm talking about the rotating cylinder viscometer, or if I'm talking about the rotating disc viscometer, or I'm talking about the concentric tube viscometer. Right? These viscometer are based on a single principle, and that principle is nothing but the Newton's law of viscosity. Right? That principle is nothing but the Newton's law of viscosity. So if I'm talking about these viscometer, right, if I'm talking about these viscometer, rotating cylinder viscometer, or rotating disc viscometer, or concentric tube viscometer, right, this is based on the Newton's law of viscosity. So I can say these viscometers are based on Newton's law of viscosity. That we will discuss later on, no? Right? That we will discuss later on. So don't worry about this, right? How this rotating cylinder viscometer works, that we will discuss later on. But time being, at least you can understand if I'm talking about these, if I'm talking about the viscometer. So these are the different types of viscometer. Which viscometer is based on the which principle, right? So the first viscometer, which is a rotating cylinder viscometer or rotating disc viscometer or concentric tube viscometer, this is based on the Newton's law of viscosity. This is based on Newton's law of viscosity, right? That we will discuss in this chapter itself. So don't worry about this. Come to the beta falling sphere viscometer, right? The second type of viscometer is a falling sphere viscometer, and this falling sphere viscometer is based on, can anyone tell me? Can anyone tell me? Falling sphere viscometer, falling sphere viscometer, can anyone tell me? Our falling sphere viscometer is based on the which principle? Can anyone tell me? Falling sphere viscometer. Beta falling sphere viscometer based on Stokes law. Based on Stokes law, right? Falling sphere viscometer based on the Stokes law. And about the Stokes law we will discuss, right? This part, Stokes law, we will discuss in the lift and drag part, right? Lift and drag part, right? This law, this Stokes law, we will discuss in a lift and drag part, right? Lift and drag, there is a one flow that is called the creeping flow. So we will discuss about the creeping flow in the lift and drag chapter. So in lift and drag chapter we will discuss about the Stokes law, right? So if I'm talking about the falling sphere viscometer, so falling sphere viscometer is based on the Stokes law. Now come to the next, which is a capillary tube viscometer, right? Capillary tube viscometer. So beta capillary tube viscometer is based on the Hagen-Poiseuille flow concept, right? It is based on Hagen-Poiseuille, based on Hagen-Poiseuille law. It is based on the Hagen-Poiseuille law. And Hagen-Poiseuille law, okay, we will discuss in a pipe flow, right? If I'm talking about the fully developed laminar incompressible fluid flow in a pipe, that is called the Hagen-Poiseuille flow. So about the Hagen-Poiseuille flow we will discuss in a pipe flow, right? If I'm talking about the syllabus, if I'm talking about the content of a course, so in a content of course I already mentioned that internal viscous flow. Remember that part, the content of a course. In content of course I already mentioned that internal viscous flow, right? And in the internal viscous flow there we will discuss three kind of flow. One is a plain Poiseuille flow, second one is a Hagen-Poiseuille flow, and third one is a Cotte flow, right? So capillary tube viscometer is based on the Hagen-Poiseuille flow, right? The next is a efflux viscometer. Next one is a efflux viscometer. And if I'm talking about the examples of efflux viscometer on the basis of this concept efflux, but the efflux is simply means mass outflow, right? Efflux means mass outflow. So on in this concept, on the basis of efflux concept, right? On the basis of efflux concept, there are a number of viscometer. So if I'm talking about the some examples, so Seebold viscometer, Seebold viscometer, Seebold viscometer, Seebold viscometer, right? Redwood viscometer, Redwood viscometer, Redwood viscometer, Engler viscometer, Engler viscometer, etc. Right? These viscometer are based on efflux concept, and efflux means mass outflow, right? Efflux means mass outflow. So if I'm talking about the Seebold viscometer, so Seebold viscometer is based on the efflux concept. Redwood viscometer is based on the efflux concept. Say Engler viscometer is based on the efflux concept. So efflux these viscometer, efflux viscometer is based on efflux concept. Efflux concept, right? And what is the efflux concept? Right, see here, see, beta, if I'm talking about the, or let us consider two beaker. I'm considering two beaker, okay? What is the efflux concept? I will show you, see here, I will explain here. So let us consider two beaker, right? This is a beaker number 1 and this is a beaker number 2. And in the beaker number 1, this is the beaker number 1 and this is the beaker number 2. In the beaker number 1, there is a water, right? In the beaker number 1, let us consider there is a water, and in the beaker number 2, there is a honey, right? Now I am putting a small hole at the bottom of this beaker. So let us consider a small hole here. Also I am putting a small hole here. Now tell me which beaker empty first. Out of these two beaker, which beaker empty first? In a one beaker, water is present. In the second beaker, honey is present, right? So if I'm talking about the which beaker empty first? Which beaker? A beaker in which water is present, na? In a beaker in which water is present, right? Yes, very good. A beaker in which water is present. So this beaker empty first and this beaker empty later on, right? And why this beaker empty first? Why this beaker empty first? Obviously because water has lower viscosity as compared to the honey, right? Why this beaker empty first? Because water having lower viscosity as compared to honey. Is it clear now? Is it clear? So beta, your efflux viscometer is based on this concept only, right? Your efflux viscometer is based on this concept only, right? If I'm talking about the time, obviously in this case time required is less as compared to this case to empty the beaker. Is it clear? So this is the efflux concept, right? This is the efflux concept, right? So your efflux viscometer, right, based on this concept. I hope you can understand this. Is it clear to everyone? Is it clear to everyone? So sometime you are getting a question in form of match the column, right? Sometime you are getting a question based on the match of column, right? One side there is a type of viscometer and another side there is a based on which principle, right? So you are getting some type of question. Okay, so I hope you can understand this. Okay, now come to the next very, very important part, which is a effect of temperature on viscosity. Effect of temperature on viscosity. So before starting this particular topic, beta, I already discussed in any fluid, viscosity is because of the two factors now. In any fluid, viscosity is because of the two factors now. In any fluid, viscosity is because of what is the first factor? What is the first factor? That is a intermolecular attraction force, between fluid molecules, right? Or simply we can say cohesive force between the fluid molecules, cohesive force, and in short I am saying this is a CF, right? Cohesive force, and in short I am saying CF, cohesive force. And the second factor is You know na cohesive force. You know na cohesive force. If I am talking about the fluid molecules, if I am talking about the fluid molecules, right? So these are the fluid molecules. So the bonding between these fluid molecules, is known as the cohesive force. Intermolecular attraction force between these molecules is known as the cohesive force. Right? Now second factor is, what is the second factor? The second factor is molecular momentum exchange. Molecular momentum exchange. Molecular momentum exchange between fluid molecules. Molecular momentum exchange between fluid molecules. And in short, I am writing as MME, molecular momentum exchange. In short, I am writing MME, that means molecular momentum exchange. So the second factor is molecular momentum exchange, right? Molecular momentum exchange means, see, if I am talking about the fluid particles, and if you see these fluid particles at the microscopic level, right? If you see these fluid particles at the microscopic level, so these fluid particles have some kinetic energy, na? These fluid particles have some kinetic energy. These fluid particles are not stationary, right? These fluid particle, let us consider this fluid particle. This fluid particle is moving with some kinetic energy or moving with some velocity and strike to this molecule, right? Similarly, this molecule strike to this molecule. Similarly, this molecule strike to this molecule. This molecule strike to this molecule, like this. So when one molecule strike to the another molecule, obviously it transfer its momentum. It exchange its momentum with another molecule. So when one molecule strike to the another molecule, it exchange momentum. Getting my point? If one molecule strike to another molecule, then definitely there is a exchange of momentum, right? So that is the momentum exchange between the fluid molecules, or we can say molecular momentum exchange, right? So these two factors are responsible for the viscosity in any fluid. Okay, now tell me guys, what happened when I increase the temperature, right? When temperature increases, when I increase the temperature, what happened with the cohesive force and what happened with the molecular momentum exchange? Can anyone tell me? Right, if I increase the temperature, so what happened with the cohesive force and what happened with the molecular momentum exchange? What happened? So when you increase the temperature, then definitely molecules are trying to move away from each other, na? Right, when you increase the temperature, then molecules are trying to move away from each other. So the bonding between the two molecules decreases, na? Intermolecular attraction force between these two molecules is decreases, na? So when you increase the temperature, then definitely this cohesive force decreases. When you increase the temperature, then definitely the cohesive force decreases. Yes, absolutely correct. What about the molecular momentum exchange? So beta, you know very well, when I increase the temperature, then the kinetic energy of the molecules increases, right? When I increase the temperature, then kinetic energy of the molecules increases. That means these molecules having higher kinetic energy, right? So if you increase the temperature, the kinetic energy of the molecules increases, and since the kinetic energy of the molecules increases, therefore that collision also increases. And if collision increases, that means more momentum transfer occurs as compared to the previous case when temperature is low. Are you getting my point? Are you getting my point? So beta, when temperature increases, then this molecular momentum exchange increases. When temperature increases, then molecular momentum exchange increases. Right? Till this point, it is clear to everyone. Till this point, it is clear to everyone. When temperature increases, the cohesive force decreases, whereas the molecular momentum exchange increases. Right? Now, if I'm talking about the liquids, right? If I'm talking about the liquids, so tell me guys, in liquid, which factor is significant? Which factor is predominant? If I'm talking about the liquids, so in liquids, out of these two factors, which factor is significant? Which factor is predominant? Which factor is predominant? Tell me. Out of these two factors, which factor is predominant? I'm talking about the predominant. I'm talking about the significant. So which factor is significant? So beta, obviously, if I'm talking about the liquids, in liquids, the molecules are closer as compared to the gases. Right? If I'm talking about the liquids, so in liquids, molecules are closer as compared to the gases. So definitely, if I'm talking about the liquids, so in liquids, cohesive force is, or cohesive force factor is significant or predominant. Right? So we can say in liquids, molecules are closer. In liquids, molecules are closer to each other. Therefore, cohesive force factor is predominant over molecular momentum exchange factor, over molecular momentum exchange factor. Right? In liquids, cohesive force factor is predominant over molecular momentum exchange factor. And we know that as the temperature increases, that cohesive force decreases. Therefore, liquid viscosity decreases as temperature increases. Right? We know that as the temperature increases, that cohesive force decreases. And since cohesive force decreases, therefore liquid viscosity decreases. Right? So this is the relation between temperature and the viscosity of liquid. When you increase the temperature, that liquid viscosity decreases. And this relation we can show mathematically also. Right? The relation between the temperature and the viscosity of the liquid, this relation we can show mathematically also. So there are number of approximations. Right? There are number of I can say there are number of relation between the temperature and the viscosity of the liquid. Right? So if I'm talking about the sum relation, so beta, this is the, or just 1 minute, that first relation, if I'm talking about the relation, that first relation is mu of liquid is equal to, this is A multiplied by right, this is just 1 minute, just 1 minute. Yes, A multiplied by e to the power minus bt. Right? That liquid viscosity, is equal to A into e to the power minus A into e to the power minus bt, where A, B, where A, B, where A, B are constant, where A, B are constant and B is greater than 0, where A and B are constant and B is greater than the 0. So if you see this mathematical expression, this is, then it is very much clear now. What is the T? The T is the absolute temperature. Beta, what is the T? The T is the absolute temperature. This relation is not important now. From exam point of view, this relation is not important. Right? I'm just showing the relation between mu and T, relation between liquid viscosity and temperature. So this mathematical expression is not important as per the exam point of view. Not important. This relation is not important. This relation, that means this mathematical expression, this mathematical expression is not, no need to remember, or I can say no need to remember. No need to remember this mathematical expression, right? No need to remember this mathematical expression. I'm just showing the relation between, right, mu and T for the liquid, right? So this is one approximation, or you can say this is the one relation between mu and T. So it is very much clear. If you see this mathematical expression, then this is very much clear. When you increase the temperature, when you increase the temperature, then definitely this mu decreases, right? If temperature increases, right, B is greater than 0, that means B is a positive constant. So when T increases, then definitely this term decreases, and we can say the liquid viscosity decreases as the temperature increases, right? So this is a one relation between the mu and the temperature, right? There is another relation also, right? This is the another relation, right? This is the another relation, and again I am telling you better, this, there is no need to remember this expression, right? No need to remember, right? No need to remember, right? This is the another relation between the mu of liquid and the temperature. So again, if you see this mathematical expression, then A, B, C are constant. Which depends on the type of liquid, right? A, B, C are constant. Depends on type of liquid. If there is a water, ABC value is different. If there is a let us consider, if there is a some oil, then ABC value is different. So ABC are the constant which depends on the type of liquid. Now if I am talking about the T naught, but the T naught is 273.15 Kelvin or 273.16 Kelvin. Right, this is the absolute zero temperature. T naught is nothing but the absolute zero temperature, right? What is the mu naught? This mu naught is the viscosity of liquid at temperature T naught, and what is the mu? Mu is the viscosity of liquid at absolute temperature T, and beta, whenever I say absolute temperature, that means temperature is in Kelvin, right? Whenever I say absolute temperature means temperature is in Kelvin, right? Whenever I say absolute temperature, so absolute temperature, that means temperature is in Kelvin. Simple. Temperature is in Kelvin scale. right? Temperature is in Kelvin scale, right? So this is the another relation. This is the another relation which shows the relation between the viscosity of the liquid and the temperature. And this relation also shows, when temperature increases, that mu of liquid, when temperature increases, mu of liquid decreases. Is it clear? Right? So I am showing one expression and I am showing another expression. Right? Is it clear to everyone, beta? Again I am repeating here. There is no need to remember these expressions. No need to remember these expressions. You must remember this part. Right? You must remember this part. As temperature increases, the cohesive force decreases, and hence cohesive force decreases, the viscosity of liquid decreases. Fine. Now come to the, so this is all about the liquid. This is all about the liquid. Now come to the gases. Come to the gases. Right? Come to the gases. So now if I am talking about the gases, so tell me guys, in gases which factor is predominant? In gases which factor is predominant? Tell me. In gases which factor is predominant? Which factor is significant? Which factor is predominant? Which factor is significant in case of the gases? Obviously, right? In case of the gases, right? In case of the gases, the molecular momentum exchange factor is predominant over the cohesive force factor. Right? Yes, very good. In gases, molecular momentum exchange factor is predominant, right? In gases, molecular momentum exchange factor is predominant over cohesive force factor, cohesive force factor, right? And we know that, as the temperature increases, what happened? The molecular momentum exchange increases, right? Therefore gaseous viscosity increases. So very simple relation. As temperature increases, gaseous viscosity increases. As temperature increases, gaseous viscosity decreases. So again this relation, right? Increasing in the viscosity of gases with respect to temperature. When you increase the temperature, gaseous viscosity increases. This relation is again shown by some mathematical approximations. So the first mathematical approximation is the power law, right? So again I am saying no need to remember, right? So that first approximation is a power law. The first approximation is a power law, that mu by mu naught, power law, that mu by mu naught of gas is equal to, right? That mu by mu naught is equal to T by T naught to the power n. Right? This is the power law, where again n is a constant, depends on type of, right? Depends on type of gases. right? For example, air. For the air, the n value is 0.7. So n is constant, which depends on the type of the gases. What is the T naught? The T naught is again absolute zero temperature. T naught is again absolute zero temperature, absolute zero temperature. That means it is 273.15 Kelvin, right? 273.15 Kelvin, right? What is the mu naught? What is the mu naught? That mu naught is the viscosity of gas, viscosity of gas at T naught, right? Mu naught is the viscosity of gas at T naught. And what is the mu? That mu is viscosity of gas, viscosity of gas at absolute temperature T, at absolute temperature, at absolute temperature T, at absolute temperature T, right? So this is the one relation between mu and T for the gases, right? This is the one expression which is a power law expression. There is another expression also, that is called Sutherland equation or Sutherland law, right? There is another law, that is a Sutherland law. There is another law, that is a Sutherland law. And as per the Sutherland law, we can write mu by mu naught for the gases is equal to, or approximately equal to, T by T naught to the power 3 by 2, T by T naught to the power 3 by 2, T by T naught to the power 3 by 2 upon T naught plus S, into T naught plus S upon T plus S, right? So this is the Sutherland equation, right? Yes, Pratik, whatever I discussed, that is important for the chemical also, right? Chemical branch, mechanical branch, civil branch, right? Whatever I discussed, that is important for the chemical branch also. Okay, Sutherland law. So this law is a Sutherland law, or this is a mathematical expression of Sutherland law, right? Now see here, in this particular equation, that S, right? T naught is same, na? T naught is the absolute zero temperature. Mu naught is the viscosity of the gas at the absolute zero temperature, right? Or at temperature T naught. Mu is a viscosity of the gas at temperature T. What is S? S is the Sutherland constant. Beta, S is the Sutherland constant. S is the Sutherland constant, right? S is the Sutherland constant, and it depends on, again, it depends on type of the gas. Depends on type of the gas, right? Depends on the type of the gas. So this law also shows the relation between mu and T, in case of the gases, Is it clear? So again, this law shows when you increase the temperature, see here, when you increase the temperature, right? When you increase the temperature, right? N is greater than 0, na? N is a positive constant. N is the positive constant. N is greater than 0. So when you increase the temperature, so gas viscosity increases. This is important. This is important. And from this law also, we can say, when you increase the temperature, then gas viscosity increases, right? And from the Sutherland law, we can conclude another important point. From the Sutherland law, we can conclude another important point. And what is that important point? That important point is gases viscosity is directly proportional to root over T. From the Sutherland law, we can conclude another important point. And what is that important point? That important point is the viscosity of the gas. Viscosity of the gas is directly proportional to root over T. Right? See how it come, how this come, right? How we can know that mu of gas is directly proportional to root over T. See here, Sutherland law, that mu by mu naught of gas is equal to, right? This is T by T naught, T by T naught, T by T naught to the power 3 by 2, T by T naught to the power 3 by 2, T naught plus S upon T plus S. Right? Now see here. Now see, we can write this T naught plus S upon T naught plus S upon T naught to the power 3 by 2 into T to the power 3 by 2 upon T plus S. Na? We can write in this way also. Na? We can write in this way also. We can write in this way also. Na? Tell me. Tell me better. Tell me. Now this T naught plus S upon T naught to the power 3 by 2. This is constant. Na? Right. T naught is 273.15 Kelvin. S is the Sutherland constant. So beta, this is constant. Na? This is constant. Na? This is constant. Na? Tell me, this is constant. Na? So let us consider this constant as a A. Let us consider this constant as a A. So we can write mu by mu naught, or I can say, see, that mu is equal to mu naught multiplied by A, right? Mu naught multiplied by A into T to the power 3 by 2 upon T 1 plus S by T. We can write in this way. We can write in this way. No? We can write in this way. Right. Now beta, see here. Now see that S by T, 1 plus S by T, 1 plus S by T is approximately equal to 1. Right. 1 plus S by T is approximately equal to 1. If I am talking about this bracket factor. So don't take tension for this bracket factor. The sum of this bracket factor is approximately equal to 1. So we can say, see here, this is the another constant. This is another constant. So simply we can say that mu of gas is directly proportional to, see here, this is T 3 by 2 minus 1. 3 by 2 minus 1. So ultimately what you are getting this, right? T to the power 1 by 2, or you can say it is directly proportional to root over T. It is directly proportional to root over T. The viscosity of gases is directly proportional to root over T. And especially we are talking about the ideal gases, na beta? Whatever the gases we considered here, we assume that is the ideal gas. So in case of the ideal gas, we can say that viscosity is directly proportional to root over T. Right. So this is very, very important. No? This is very, very important. This is important. So forget about the Sutherland law. There is no need to remember this expression. No need to remember this Sutherland law. But what is important? This is important and this is important. Right? The viscosity of gases is directly proportional to root over T. But we can conclude this result, alright, we can conclude this result by kinetic theory of gases also. Right? We can conclude this result that viscosity is directly proportional to root over T from kinetic theory of gases also. Right? From kinetic theory of gases also. See here. See, if I am talking about the kinetic theory of gases from kinetic theory of gases, right? From kinetic theory of gases. From kinetic theory of gases. If you don't know about the Sutherland equation, no problem, right? We can conclude, right? We can conclude this result, or we can write this result by using the kinetic theory of gases also. See, if I'm talking about the kinetic theory of gases, let us consider this V. What is the V beta? This V is a mean travel. This is the mean travel velocity of molecules. Mean travel velocity of molecules. Right? What is the V? That V is a mean travel velocity of the molecules. Right? So definitely if V is more, then definitely the kinetic energy is more. Na? If V is more, if V increases, then definitely beta kinetic energy of the gases increases. Na? And if kinetic energy of gases increases, then molecular momentum exchange increases. Na? And when molecular momentum exchange increases, then gases viscosity increases. Na? Tell me how, yes or no? When mean travel velocity of the molecules, when mean travel velocity of the molecule increases, then kinetic energy increases. If kinetic energy increases, then molecular momentum exchange increases. And when molecular momentum exchange increases, then viscosity of the liquid increases. So beta, can I say gases viscosity is directly proportional to the mean travel velocity? Can I say beta? Can I say gases viscosity is directly proportional to mean travel velocity of the molecules? Of gas molecules, na beta, of gas molecules. Can we say that gases viscosity is directly proportional to mean travel velocity? Fine, na? Okay, good. Now see, if I'm talking about the mean travel velocity, so as per the kinetic theory of gases, what is the mean travel velocity? That mean travel velocity is 3r bar T upon molecular weight of gas. See, what is the V? That V is root over 3r bar T upon molecular weight of the gas. Sir, what is the R bar? What is the R bar? Beta, this R bar is a universal gas constant. This R bar is a universal gas constant. Universal gas constant, which is equal to 8.314 kilojoule per kilomole Kelvin. Right, this is the R bar. This is the R bar. Now, what is the T? The T is the absolute temperature. What is the T? The T is a absolute temperature. And beta, I already told you, whenever I say absolute temperature, that means in Kelvin. In Kelvin. Right. What is the, this is the molecular weight. No? It is understood. Right. This is nothing but the molecular weight of the gas. This is the molecular weight of the gas. Molecular weight of the gas. So we can say, see here, we can say get the gas viscosity, right? Viscosity of gases is directly proportional to V, and V is directly proportional to, for a particular gas, So for a particular gas, this molecular weight is constant. Na? R bar is already constant. That is the universal gas constant. Right? For a particular gas, the molecular weight is constant. So directly we can say, it is directly proportional to root over T. The viscosity of gases is directly proportional to root over T. Right? So we can write this by using the kinetic theory of gases also. By understanding the kinetic theory of gases, we can write the viscosity of gases is directly proportional to root over T. Okay, so I hope you can understand this. Is it clear to everyone? Is it clear to everyone? Type in a chat box. Crystal clear? Clear or crystal clear? Tell me. Beta, clear or crystal clear? Clear or crystal clear? It is simply clear or crystal clear? Okay, now. Okay, now see the question. Question number 1. Question number 1. As the temperature increases, viscosity of fluid. As the temperature increases, viscosity of fluid. Option A increases. Option B decreases. Option C may increase or may decrease. And option D is constant. Right? As the temperature increases, then what happened with viscosity of the fluid? What happened with viscosity of the fluid as the temperature increases? Okay, so what is the answer? The correct answer is Chennai. C is the correct one. The correct one is C, Chennai. C is the correct one, beta. C is the correct one. See, if I'm talking about the fluid, so fluid may be liquid, may be gases, na? Here I am saying fluid. I'm not saying liquid or I'm not saying the gases. I'm saying fluid. So the fluid may be, right? Fluid may be gas, may be liquid. Fluid may be gas. Fluid may be gas. Fluid may be gas. May be liquid, na? May be liquid. Right? Fluid may be gas, may be liquid. Right? And we know that as temperature increases, that gas viscosity increases, and we know that as temperature increases, liquid viscosity decreases. So what is the correct answer for this question? The correct answer is C. If in a question gas is mentioned, as temperature increases, viscosity of the gas. If gas is mentioned, then answer increases. In this question, if instead of the fluid, liquid mentioned, right, then what is the correct answer? Correct answer is Bombay. But in this particular question, fluid is mentioned, right? If fluid is mentioned, then definitely, then viscosity may increase, may decrease. It depends on the, right? It depends on the fluid is liquid or gas. So correct answer is Chennai. C is the correct one. Okay. Now come to the question number 2. Come to the question number 2. Let us consider two substances. Let us consider two substances. A and B, right? And rho A is greater than rho B. Rho A is greater than rho B. Rho A is greater than rho B. So if rho A is greater than rho B, then option A, mu A is greater than mu B, right? Viscosity. Viscosity of A is greater than viscosity of B. Option B, viscosity A is lesser than viscosity of B, right? Option C, viscosity, right, mu A is greater than mu B, or mu B is greater than mu A, right? And option C or option D can't comment, or I can say none of this. Okay, no problem. None of this, right? So let us consider two substance. Let us consider two substance, substance A and substance B. Let us consider two substance A and B. And what is the relation between density of A and B? Rho A is greater than rho B. Then mu A is greater than mu B, right? Mu A is greater than mu B, or mu A is lesser than mu B. Option C says mu A is greater than mu B is also possible, and mu B is greater than mu A is also possible, right? Mu A is greater than mu B, that is also possible, and mu B is greater than mu A, that is also possible. And option D says none of this. What do you think? Option A, option D. Okay. Okay. But first try to understand. First try to understand. See, rho is a density, na? Rho is a density, right? Rho is a density, and mu is the viscosity. What is the physical significance of the density? What density measures actually? What actually density measures? Right? What actually density measures? What is the significance of the density? Right? It measures the inertia. Right? It shows the inertia. Right? Measure of inertia. Measure of inertia. Right? Rho shows measure of inertia. Right? If rho is more, that means inertia is more. What is the mu? Mu is the viscosity which measure resistance against the flow. Measure resistance against the flow. Against the flow. Is it clear now? Okay. Now see here. Now see here. I am showing some values. See this table. This table is visible to everyone. Beta, this table is visible to everyone. This table is visible to everyone. This table is visible to everyone. Visible, na? Now, see here. Let us consider gasoline. Let us consider gasoline. See, I'm sorry. Let us consider gasoline. Right? Let us consider gasoline. What is the density of gasoline? 680 kg per meter cube. Right? What is the density of gasoline? 680 kg per meter cube. And what is the viscosity? That is 2.92 into 10 to the power minus 4 kg per meter second. Now consider water. Where is the water? This is the water. See? Water. Right? For the water, what is the density? Let us consider 998 kg per meter cube, corresponding to 20 degrees Celsius. And what is the viscosity? That is 1 into 10 to the power minus 3. Okay, fine. We can write, just 1 minute. Use this table. So I am giving example of gasoline. Gasoline means petrol, na? Gasoline and water. Right? In Europe side, petrol is called gasoline. So gasoline and water. So if I am talking about the density of gasoline, everyone knows better, gasoline density is lesser than the density of water. Right? Density of water. So let us consider water density corresponding to 20 degrees Celsius, that is 998 kg per meter cube. right? And everyone knows that gasoline density is lower than the water density. So what is the density of gasoline? What is the density of gasoline? In this table it is mentioned 680. 680, right? This is 680 kg per meter cube. Okay, now come to the viscosity of water, right? And come to the viscosity of gasoline. What is the viscosity of gasoline? What is the viscosity of gasoline? See here, what is the viscosity of gasoline? 2.92 into 10 to the power minus 4. 2.92 into 10 to the power minus 4 kg per meter second, right? And what is the viscosity of water? We know 1 into 10 to the power minus 3. So we can write directly 1 into 10 to the power minus 3, or we can write 0.1, or we can write in this way 0.1 into 10 to the power minus 4 kg per meter cube. I'm sorry, kg per meter second. Is it okay now? Now compare density of gasoline, right? Density of gasoline or density of water versus density of water to density of gasoline, right? That is equal to greater than 1, obviously greater than 1. This is 998, this is 998 upon this is 680. And if you compare the viscosity of water to viscosity of gasoline, right? So viscosity of the water 0.1 into 10 to the power minus 4, and this value is 2.92 into 10 to the power 2.92 into 10 to the power minus 4. So minus 4 minus 1 is cancelled out, and see here 0.1 by 2.92, 0.1 by 2.92. So 0.1 by 2.92, 0.1 by 2.92, right? This is 0.0342, and this is greater than 1 beta. This is greater than 1 na? This is greater than 1. Or you can write here, right? 998 divided by 680. So this comes 998 divided by 680. So this is 1.46. So see here, the density of water is greater than the density of gasoline, right? Density of water is greater than the density of gasoline, but viscosity of water is lesser than the viscosity of gasoline, right? So this is the one possibility. What is there is another possibility? The another possibility is that viscosity of, see, this is also possible beta, this is also possible, both are possible, right? This is also possible, right? Here I am comparing the gasoline and the water, right? If you compare the water and the mercury, or if you compare the water and the water and some oil, getting my point? So both are possible. This is also possible, right? So don't think so if density is more, then viscosity is also more. No, it is not like that, right? Density is a different thing and the viscosity is different thing. Density is a measure of inertia. Right? Density shows in a given volume, number of molecules, right? In a given volume, number of molecules are more. Density is more, right? Whereas that viscosity shows, if I'm considering some molecules, right? If I'm talking about the, let us consider if I'm talking about the liquid. If I'm talking about the liquid, so that viscosity shows what is the cohesive force between that two molecules, or what is the cohesive force between the molecules of the liquid. Is it clear to everyone? Is it clear or not? Is it clear or not? So what is the correct answer? Correct answer is C. Chennai. C is the correct. C is the correct one. Is it clear or not? Tell me, guys. Is it clear or not? Is it clear or not? From this graph, I am comparing. See, I am comparing gasoline and the water. Now you can compare gasoline and benzene. You can compare gasoline with ammonia. In some cases, what you are getting mu A is greater than mu B. In some cases, what you are getting mu A is lesser than mu B. Right, so I hope you can understand this. This is a very, very important interview question. This is very, very important interview question. This is an interview question. Right, this is very, very important interview question. Right, and also understand this. Right, density shows measure of inertia. If in a given volume number of molecules are more, then density is more. Right, if I'm talking about the liquids, if cohesive force between the molecules is more, if the intermolecular attraction force between the molecules is more, then viscosity is more. Okay, fine. Okay. Now question number 3. Now come to the question number 3. Question number 3. No, so this is the shear stress versus tau versus d phi by dt graph. Right, shear stress versus shear strain rate plot. Now this is the just 1 minute. Okay. Okay, so which graph is for water and which graph is for air? Let us consider two substances. One substance is water, another substance is air. No, beta, no, it's wrong. It's wrong, Manthan, it's wrong. If number of molecules are higher, it doesn't mean the cohesive force between the molecules is high. No, it's wrong. Right? It's wrong. Right? See here. इसको थोड़ा सा सिंपल वर्ड में समझते हैं, ठीक है? आपको हिंदी आती है, इसलिए मैं आपको हिंदी में समझाता हूँ. सिंपल है. देखो, मान लीजिए, just take an example. Let us consider in my Facebook, right? In my Facebook, there are 4,000 number of friends. ठीक है, मेरे Facebook में 4,000 number of friends है. In my Facebook, 4,000 number of friends. ठीक है, so number of friends are 4,000. बट क्या उनके साथ जो बॉन्डिंग है, ठीक है, उनके साथ जो बॉन्डिंग है, क्या वो 4,000 जस्टिफाई कर रहा है क्या, या वो 4,000 बता रहा है क्या? Right? Again I'm repeating. It doesn't mean beta अगर आपके पास see if number of molecules are more. Let us consider in case number A. Right? These are the number of molecules. In case number B. So definitely we can say that density of A is greater than density of B. We can say density of A is greater than density of B, because in a given volume, right, let us consider this is the given volume, and here also this is the given volume. right? So in a given volume, in the case number A, right, number of molecules are more. So density of A is greater than density of B. But what about the intermolecular attraction force? Intermolecular attraction force. Intermolecular attraction force means intermolecular attraction force means force between two molecules. I am talking about the two molecules. Two molecules. Right? I am talking about the bonding between two molecules. Might be possible. Here the bonding are less. Right? In this case, bonding is more. In this case, bonding is more. Right? So might be possible. I am saying might be possible. Might be. Right? Might be possible in case of A, cohesive. In case of A, cohesive force is lesser as compared to case B. Is it clear? Is it clear or not, Manthan? Is it clear or not? Is it clear or not? I am talking about the possibility beta. No, I'm not saying it happen. I'm not saying it happen. It may be happen. Right? Might be cohesive force A is greater than cohesive force B, but the cohesive force A is lesser than the cohesive force B. That is also possible. That is also possible. Is it fine? So here I am comparing the two fluids. Please focus. Here I am comparing the two fluids. Here I am comparing the two fluids. Right? Here I am comparing the two fluids, and again I am saying, right, in this case the cohesive force is the intermolecular attraction forces between the two molecules, whereas the density represents the number of molecules in a number of molecules in a given volume. So please try to understand this. Number of molecules more, that doesn't mean the bonding between the molecules are more. Right? Number of molecules more doesn't mean number of molecules more doesn't mean the bonding between two molecules are more. Okay. Now come to the question number 3. Now see here. The graph number 1. Graph number 1 is for graph number 1. Sir, which one is the graph number 1? This is the graph number 1. Let us consider this is the graph number 2. Graph number 1, graph number 2. Graph number 1 is for yes, graph number 1 is for the water, right? If I am considering the water and the air, so graph number 1 is for the water and the graph number 2 is for the air. So we know that viscosity of the water is lesser as compared to the viscosity of the air. We know that. Now let us consider angle between these two, right? This angle is theta, right? Let us consider this angle is theta. So beta, tell me, when temperature increases, what happened with theta? When temperature increases, what happened with theta? When temperature increases, then what happened with theta? That option A, increase, option B, decrease, option C, does not change, and option D, none of this. When temperature increases, then what about the theta? Tell me. When temperature increases, then what about the theta? Okay, see. But when temperature increases, then See, if I'm talking about the water, if I'm talking about the water, if I'm talking about the water, as the temperature increases, that water viscosity decreases, whereas temperature increases, then air viscosity increases. We know this, na? We know this, right? And slope represent the in tau versus d phi by dt graph, slope represent the viscosity. Slope represent the viscosity, right? Now see, so when you increase the temperature, that means for the heated water, this is the graph. For heated water, this is the graph. For heated water, this is the graph, right? This graph is for heated water. This graph is for heated water. This graph is heated for heated water, right? Viscosity decreases. That means this slope, na, earlier this is the slope, now this is the slope. So slope decreases. Why slope decreases? Because viscosity decreases, and slope represent the viscosity. And when temperature increases, air viscosity increases. Air viscosity increases. So this is the graph for the heated air. This is the graph for the heated air. This is the graph for heated air. This is the graph for the heated air. So earlier this angle between these two graphs is theta. Now after heating, this is the angle. So let us consider this is the theta dash, and it is clearly, right, it is clearly you can say, right, theta dash, clearly you can say theta dash is lesser than the theta. Theta dash is lesser than the theta. Clearly you can say. So what happened with theta? So when temperature increases, that theta decreases. So what is the correct answer? Correct answer is Bombay. Correct answer is Bombay. Is it clear? Is it clear or not? Abhinav, clear? Abhinav says increase. No beta, it decreases, na? It decreases. Okay, very good, very good. Very good. Okay. Now, come to the, here we discuss about the effect of temperature on viscosity. Now come to the effect of pressure, right? So far we not comment on the effect of pressure on the viscosity, right? So beta, if I'm talking about the effect of pressure, right, the effect of pressure on the viscosity of the fluid is negligible, right? The effect of pressure on viscosity of the fluid is negligible, or we can say, right, the pressure effect of pressure on viscosity of the fluid is very small, very small, right? So see, if I'm talking about the liquid, see here, if I'm talking about the liquids, for liquids we generally treat liquid as an incompressible, na, right? Generally liquids are treated as an incompressible, na. I already discussed in the I think session number 1 or session number 2. I already discussed in the session 1 or session 2. I'm not exactly it is not exactly known, but yes, we know that for liquid or we'll consider liquid as we consider liquid as incompressible, right? So better, when you increase the pressure, when pressure increases, when pressure increases, what happened? The intermolecular attraction force between the liquid molecules, right? Liquids are generally treated as incompressible. So when pressure increases, what happened with the intermolecular attraction force? What happened with the intermolecular attraction force? Because what happened? So beta, cohesive force does not change much. Cohesive force does not change much. Right? When pressure increases, cohesive force does not change much. Right? Beta, when you say incompressible, that means it is difficult to compress, na? When you say incompressible, that means it is difficult to compress, na? And if it is difficult to compress, that means there is it is difficult to change the cohesive force, na? The cohesive force not changes, but it changes, but it changes very little amount, or I can say it not changes much. Right? There will be slight change. Yes. So for liquid, right? For the liquid, when you increase the pressure, then cohesive force does not change much. Therefore, viscosity of liquid does not change when pressure increases. So I hope you can understand this. Now second point, if I'm talking about the gases, beta, so in case of the gases, that viscosity is only function of temperature. Right? In case of the gases, we already discussed about the gases. See, if I'm talking about the gases, in gases, viscosity is because of molecular momentum exchange. Molecular momentum exchange is because of the mean travel velocity. Right? Because of the mean travel velocity. Please try to understand this. Right? And this mean travel velocity is a function of temperature, not function of pressure. See here. See this mathematical expression. In this mathematical expression, pressure is present or not? Pressure is not present. So in case of the gases, the viscosity is a function of kinetic energy, and kinetic energy depends on only pressure. Kinetic energy only depends on the pressure. Kinetic energy only depends on the temperature. It does not depend on the pressure. Is it clear or not? So for gases, right? In case of gases, viscosity only depends on temperature. Only depends on temperature. Only depends on the temperature. Does not depend on the pressure. Right? Does not dependent or does not depends on the pressure. Does not depends on the pressure. So I hope you can understand this. See, beta, when I talking about the gases, pressure is directly proportional to temperature. Who says here? Pressure is directly proportional to temperature. Who says? Please try to understand the things. Come to here. Beta, when I talking about the kinetic theory of gases, so in kinetic theory of gases, this mean travel velocity is only function of temperature. Right? This mean travel velocity is only function of temperature. It does not changes with pressure. It only function of the temperature, mean travel velocity. So we can say this Gases viscosity is directly proportional to temperature only, na? Temperature only. The gases viscosity is directly proportional to temperature only. Directly proportional to temperature only. See here already I prove. The viscosity of the gas depends on the mean travel velocity. And mean travel velocity depends on the only temperature. Right? Pressure is present here? No. Also, if you see this mathematical expression, pressure term is there. If you see this mathematical expression, pressure is present. No, pressure is not present, na beta. So these relation also shows viscosity does not dependent on the pressure, or very slightly dependent on the pressure, very slightly. This relation also tell us, right? Theoretically we can say as well as mathematically we can say. Theoretically we can justify our statement, as well as mathematically we can justify our statement. Is it clear, Sahib? Is it clear or not, beta? Is it clear or not? So in case of gases, viscosity only depends on the temperature, only depends on the temperature. So if you change the pressure, viscosity does not change. Right? So that's why I'm writing here, this is the important point, the effect of pressure on viscosity of the fluid is negligible. Effect of pressure on viscosity of the fluid is negligible. So I hope you can understand this. Okay, fine. Okay, so I think this is enough for today. Okay, so this is your homework question, right? This is your homework question. Anyone try this question? Anyone tried this question? What is the answer? What is the answer? This is a simple question. This is a simple MCQ question. What is the answer? The velocity distribution for flow over a flat plate is given by 4/3 y minus y to the power 4/3, where u is the fluid layer velocity in meter per second, right? Where u is the fluid layer velocity in meter per second at a distance y meter above the plate. The shear stress at y is equal to 6 centimeter above the plate is, okay, fine. So this is the plate, and above the plate fluid is flowing. Above the plate fluid is flowing. This is the x direction and this is y direction, right? This is x direction, this is y direction. And if you see the velocity profile, so this is the velocity profile, and it is given u is equal to 4/3 y minus y to the power 4/3, right? And dynamic viscosity is given. Mu is equal to 8 poise, or we can write 0.8 Newton second per meter square, right? 8 poise or 0.8 Newton second per meter square. Fine. Now if you apply the Newton's law of viscosity from Newton's law of viscosity, we can write the shear stress at any y is equal to mu du by dy at that y. right? Now u is given. Now calculate du by dy. So du by dy is equal to, this is 4 by 3 minus 4 by 3 minus, right, x to the power n, n x n minus 1. So y to the power, just 1 minute, 4 by 3, and this is 4 by 3 y to the power 4 by 3 minus 1. So this comes 4 by 3 minus 4 by 3 into, this is y to the power, right, 1 by 3, 1 by 3, right? This is du by dy. This is du by dy. So tau at any y is equal to mu du by dy at that y, right? And du by dy we already calculated, du by dy, and this is equal to 4 by 3 minus 4 by 3 into y to the power 1 by 3, right? This is du by dy. Fine. Now at which layer shear stress is asked? At y is equal to 6 centimeter. At y is equal to 6 centimeter, but in this expression y is in meter. So at y is equal to 0.6 meter. Shear stress at y is equal to 0.06 meter, and this is equal to, so mu is given, that mu is 0.8 multiplied by du by dy. So this is 4 by 3 minus 4 by 3 multiplied by, this is 0.06 to the power 1 by 3, right? So from here you are getting tau at y is equal to 0.06 meters. So what is the answer? What is the answer? That option D, that is 0.65 Pascal. Everyone getting this answer? 0.65 Pascal. Everyone getting this answer? 0.65 Pascal. Okay, now tell me where the shear stress is maximum. Where the shear stress is maximum. Every layer experiences the same shear stress. In this problem, every layer experiences the same shear stress. In this problem, every layer experiences the same shear stress, or each layer experiences a different shear stress. Yes, each layer experiences a different shear stress. But each layer experiences a different shear stress. If you see this mathematical expression, see mu is same for each layer, na? Mu is same for each layer. Now this du by dy is different for the different layer. This velocity gradient, this velocity du by dy is different for the different layers. Are you getting my point? Right? See, du by dy is a function of, beta du by dy is a function of y, na? Du by dy is a function of y. Right? So definitely if du by dy is a function of y, and as we are moving away from the plate, right? As we are moving away from the plate, right? So definitely that y value changes, y value increases. Right? As we are moving in a y direction, as we are moving in this direction, that y value increases. And y value increases, beta, y value increases. See this mathematical expression. If y increases, then definitely this du by dy decreases. When y increases, du by dy decreases, and du by dy decreases, therefore tau decreases. So as we are moving in the y direction, the shear stress value decreases. That means maximum shear stress occurs at the y is equal to 0. Right? Maximum shear stress occurs at y is equal to 0. So calculate maximum shear stress. Calculate maximum shear stress. So maximum shear stress occurs at y is equal to 0. Y is equal to 0. So tau maximum, or you can say tau wall, or you can say tau at y is equal to 0. So calculate tau at y is equal to 0. So it is simple, na? This is 0.8. multiplied by y value is 0, so it comes 4 by 3. It comes 4 by 3. Right? So calculate this in Pascal. Right? So shear stress is maximum at y is equal to 0. Shear stress is maximum at y is equal to 0. Right? That means surface experiences the maximum shear stress. Right? Surface experiences the maximum shear stress. Is it clear to everyone? Is it clear to everyone? Is it clear or not? Right, come to this question. The velocity distribution in a 1 centimeter dia pipe is given by, okay, fine. So this is the pipe and this is the radial direction, right? This is the radial direction. This is the radial direction. R naught is the pipe radius. This is the R naught. This is the MSQ question. Na? This is the MSQ question. So pipe radius is R naught and the velocity variation with R is given. Which one or more of the following statement are true? Take viscosity of the water as a 1 centipoise. So U of R is equal to, this is 16, 1 minus R square by R naught square. Right? That means parabolic velocity profile. The parabolic velocity profile. Now question asks shear stress at the center line is 0. Statement A says shear stress at the center line is 0. Statement B says shear stress at the center line is 6.4 Newton per meter square. Shear stress at the wall is 0. Right, and the shear stress at the wall is 6.4 Newton per meter square. So I already explained shear stress at the wall is the maximum. Right, in the previous question I already explained the shear stress at the wall is maximum. Shear stress at the wall is maximum. So shear stress at the wall is 0. This is wrong. This is absolutely wrong. Shear stress at the wall is 0. That is absolutely wrong. Shear stress at the wall is maximum. Now see here. If you write the Newton's law of viscosity. If you write the Newton's law of viscosity, so Newton's law of viscosity, that tau at any y is equal to, that is mu du by dy, mu du by dy at that, sorry, at that y, mu du by dy at that y. Right, now y is taken from the wall, surface, from the surface, y is taken from the surface. So beta, can we modify this equation? Can we modify this equation, this Newton's law of viscosity, for the pipe flow, where R is taken from the center line? Can we modify this equation? Can we modify this equation for the pipe flow where R is taken from the center line? Yes, we can modify. See here. Can I write beta? See here. Let us consider a fluid layer. Let us consider this fluid layer. Okay, so this from the wall, this fluid layer is at a distance y, whereas from the center line, this fluid layer at a distance r. Right, from the wall, this layer is at distance y, and from the center line this layer is at a distance r. So we can write now that r plus y is equal to r naught. R plus y is equal to r naught. Yes, we can write. Right, now from here we can write dr plus dy is equal to 0 because r naught is constant. So dr plus dy is equal to 0. So simply dy is equal to minus dr. Dy is equal to minus dr. Right, now modify this equation. So if you modify this equation, the shear stress at any radial distance r, where r is taken from the center line, shear stress at any radial distance r, that is equal to minus mu du by dr at any r, right? And r is taken from where? From center line of pipe. Is it fine? Okay, now see here, u of r, that u of r is equal to, this is 16, 1 minus r square by r naught square. Now calculate du by dr. So if you calculate du by dr, this is 16, 0 minus, this is 2r by r naught square. Right? Now see, at the center line means at r is equal to 0, at r is equal to 0, that du by dr is 0. At r is equal to 0, that du by dr is 0. So at r is equal to 0, du by dr is 0. If du by dy is 0, so at r is equal to 0, the shear stress is 0. That means at the center line, the shear stress is 0. At the center line, the shear stress is 0. At the center line, shear stress is 0. So shear stress, A is correct. Na? A is correct. Shear stress at the center line is 0. A is correct. B is wrong. Right? B is wrong. C is also wrong. Now shear stress at the wall. Now come to the shear stress at the wall. So at the wall means tau at r is equal to r naught. So this is minus mu into, this is minus 16 into 2 by 2 r naught by r naught square. Right? Now r naught and r naught is cancel out, so it is simply 16 mu, no 16, it is 16 to the 32 mu divided by r naught, right? And 32 multiplied by, what is the value of mu? Mu is 1 centipoise. 1 centipoise, that means 0.1 Newton second, right? Mu is 1 centipoise. I'm sorry, 1 centipoise. See, 1 centipoise means 1 into 10 to the power minus 2 poise. See here, na? 1 centipoise means 1 into 10 to the power minus 2 poise, or we can say 10 to the power minus 2 into 10 to the power minus 1 Newton second per meter square. Right? So this is 10 to the power minus 3 Newton second per meter square. Right? So this is 32 into 10 to the power minus 3 divided by, what is the R naught? Pipe diameter is 1 centimeter. 1 centimeter dia. So 1 centimeter dia, that means radius is 0.5 centimeter. So 0.5 centimeter means 0.5 into 10 to the power minus 2. Right? So it comes 32 divided by, right, 10 to the power minus 2, 10 to the power, and this is 5. And 5, 6 and 4, right? So 6.4 Newton per meter square. 6.4 Newton per meter square. Yes. So shear stress at the wall is 6.4 Newton per meter square. So correct answer is A and D. Right? So this is the MSQ question. So correct is A and D. A and D both are correct. Fine. So I think this is enough for today. Tomorrow we will discuss another fluid property, that is a kinematic viscosity, and also we will discuss about different application related to the Newton's law of viscosity. Right? So tomorrow we will discuss. I think tomorrow is tomorrow is no class. Day after tomorrow. Right? Day after tomorrow. Okay, so thank you so much guys. Bye bye, take care and good night everyone.